Thanks to the 2019 Ridgecrest sequence, there's been a lot of interest in the question of how dynamic rupture propagates through orthogonal strike-slip fault systems. So as we know in Ridgecrest, there was one earthquake on a left lateral fault, followed the next day by an earthquake on a right lateral fault at nearly 90-degree angle away from it. But that's just one possible behavior that can go through a fault system like this. You can also have one where rupture propagates down one fault of the system and just passes the other one as if it's not even there, as happened with the 92 Landers rupture passing the Pinto Mountain fault as if it didn't exist. Or on the other hand, you can have a rupture that propagates through both faults of the component system. Something like the 2012 off Sumatra earthquake, which zigzagged through a massive network of orthogonal strike-slip faults. So here I'm using the 3D finite element method to conduct dynamic rupture simulations of ruptures across simplified orthogonal strike-slip fault systems. So all of my component faults are planar and vertical strike-slip faults, and in a homogeneous elastic half space. And this is just step one, though. Eventually, I'm going to vary some more aspects of the surrounding. But for now, my basic fault geometries are I have a vertically oriented 60 kilometer long fault, which I'm going to call the vertical fault. They all have vertical dips. And then a 30 kilometer long other fault that splays off of it from the middle, either to the right or to the left. And I'm going to call that the horizontal fault, although it also has vertical dip. And I also then have some plus sign shaped fault systems. And the reason I have two different ones here is just that our method doesn't allow two mutually cross-cutting faults. One has to be discontinuous at the junction. So I have one where the vertical fault is continuous and the horizontal is discontinuous, and then vice versa. And for each of these cases, I test nucleation points at all of the ends of the limbs of the system. I test combinations of a high stress state and low stress state, shown in this table up here. And I also vary which fault is right lateral and which is left lateral. So all said and done, you get a suite of 28 simulations when you combine all of that parameter space. And I got three major rupture behaviors, and they correspond with those examples that I mentioned before. So I have some ruptures that just stay on the nucleation fault and completely ignore the second fault. I have some two-fault ruptures that propagate from the nucleation fault onto part or all of the second fault. And I count even a partial one as a two-fault rupture. Or some where you have rupture stays on the nucleation fault but causes a bit of triggered slip on the second fault, which I think is comparable to the Ridgecrest 6.4, which at least activated a right lateral cross fault enough to cause a bunch of aftershocks on it. So down here on the poster, this maze of lines is just a cartoon representation of the different ruptures across parameter space. I will let you peruse that at your will, but I'm going to get onto some take-home points. One is that if you have a stopping phase from the rupture on the first fault hitting the second fault, or rather, if the first fault stops at the second fault will rupture. The shear stress changes from rupture stopping are strong enough that they will set off that second fault, just like you're shooting an arrow right at it. And that's going to overcome any dynamic normal or yield stress changes from other processes. So any rupture that starts on the short arm of a T-shaped fault will propagate onto the second fault. And also any rupture that begins on one of the discontinuous fault arms of a plus-shaped system is also going to activate the second fault. Next, the initial stress state on the second fault is a really controlling factor. So if you have a rupture that starts on a low stress fault, it's not going to cause enough stress perturbation to activate the high stress one. And it's probably not going to be able to cause more than triggered slip on another low stress fault. But if you have a rupture that starts on a high stress fault, it's going to be able to go kind of whichever way it wants, depending on what happens in this last point. So the last thing is that the first direction of slip from the first fault makes a difference. So for example, in the case of a rupture that starts at the northern end of a right lateral fault, it's going to compress the junction. And that's going to increase the yield stress here really hard. So rupture isn't necessarily going to be able to go onto the second fault. By the time you get into extension here, the rupture front is already passed. Meanwhile, on the other hand, if you start here on the bottom, you get extension first. And that opens up this limb and allows the rupture to continue, even though you get compression acting on this fault later.